Is it Monday? I feel that I sound like Darth Vader with this microphone.
If we hold a vote, can we go back to Friday?
Keep Friday evening continuously. Yeah, good morning, Steven.
Good morning, Professor.
Oh, you're selecting a seat away from the whiteboard, so there will be less temptation to ask you right equations, right? Okay, well, thank you for keeping coming. When we meet on Wednesday, please don't forget to bring your computers. Again, today it's, I don't care. By the end of the meeting, please write your name on these pieces of paper and try to fill them to your best understanding. So it's kind of surprise quiz. But do not fear, because it will be absolutely based on the material in class. And so it is 759 course, right? Whatever index is. Part 1 physical chemistry, part 1 quantum, which we should complete in by the beginning of March. We agreed to make it project-oriented course, and no one was objecting when we decided to study two-dimensional hydrogen molecules, like their dissociation. As we go toward this goal, we need practical skills, which we will get on Wednesdays for using MATLAB, and it is a shortcut to avoid the analytical derivations, which are kind of natural part of physical chemistry and quantum discipline, but it's not possible to get a substantial leap through in 2 months. So we'll just let computers to do our job as much as possible. Also, I'm not hiding that this survey course uses some materials prepared for the long course. And today will be a specific part of material which typically belongs to the very last or second last lecture in the regular course. So in some sense, it is relatively advanced. If we are looking for traditional style of learning from simple to complicated, then I'm doing the very wrong thing today. But if we do a project-oriented course, I do not want to do too much intrigue and want to play open cards. So the concepts that we will cover in today's meeting will be used towards completion of the project. And from my experience in previous longer classes, typically at the last or second last lecture, no one cares about material and it's wiped off the memory right away. Right now, we do not have background for the material that I'm going to deliver, but it will be in some sort, how to say, invitation or prompt what we should look at and which material we should absorb more intense when it will be time. So please do not develop irritation, do not object and do not complain that the material is a little harder than expected. I realize it myself. So I'm jumping right away to the one of the most complicated things. But it's not, I'm not posing a goal to ask everyone to memorize and go over exam. We are doing project. It's mostly like an overview. Basically, what is the goal of this course? Making a survey of advanced concept. And later on, after we see what our knowledge lacks, we can complement. It's like making the blueprint of a building and then putting bricks. So we, to do blueprint, we do not need to have all foundation. Okay. I will try to remember and invite you to fill these little quizzes. But if I forget to do so, please do not wait. As soon as the material sufficient for filling these tables and a little figure on the back side, as you feel you can do it, please do not hesitate and try doing your best. I hope that I will control myself and remind you, but if I don't, just work on it. It will help our mutual benefits. So I will see if I delivered something wrong and I need to change the pace, and you'll give me the signal, like, oh, is it right style of communications? So it's not to assess your knowledge, it's mostly assess our communication channel. Okay, when we met for the first time, we did this little chart, making a rough plan that we are looking onto interstellar molecular gas in nebulas that is getting excited, ionizes first electron, then H2 plus is photoexcited, and then it dissociates, and then the proton from this dissociation, good morning, and electron recombine and generate emission that one can observe in the telescope. So where are we now at this little map? We are going to get some concepts related to absorption of light by a molecule. And there are some conceptual features that all of you who ever deal with UV visible spectroscopy will realize. Maybe some of the concepts that I declare as advanced are natural for some of you, especially if anyone does everyday UV spectroscopy, it will be quite natural. So the main idea that we are going to cover today, and you can assess it with your own vision, either entertain or torture you with lots of equations. But the idea behind them is that when we have molecular system, we have both electronic and nuclear degrees of freedom, right? There are interatomic distances and there are positions of electrons. And when you try to probe, to excite this molecule with a photon, with light, right? The way, the pattern, how it will be excited from ground to excited does depend on not only on electronic clouds and molecular orbitals, but also on interatomic positions. And since everything is so probabilistic, there is a probability for atoms to be closer or further away, and this probabilistic thing go on simultaneously. The spectra, the response of a molecule to light excitation of different frequencies will depend on probabilistic nature of interatomic distances. And we'll have some features that can be observed by spectroscopy, just by relatively inexpensive instrument related to variation of interatomic distances. So what if I imagine myself on your side? Which associations I may develop with this little motivation talk? I may think like, he is telling about spectroscopy and I am doing everyday spectroscopy with NMR. It's definitely something different. Another thought, he is talking about interatomic distances. Interatomic distances are typically related to normal modes and Fourier transform infrared spectrum. And now I'm confused. Is he speaking about infrared or UVVs? And the third way, I don't care. It's all noise that I just want to wait 1 hour and leave. So did my feedback click on something? You see a little misconception and disagreement. So it is not about NMR. It is not about infrared or Raman. It is just UVVs, the visible range. But visible range and ultraviolet spectra also depend on interatomic positions. And this is the thing that I'm going to speak about. Make sense, or there are some objections? Okay, feel free to stop me. So this is a review of what we did on our first meeting, right? So if we have this interstellar molecular hydrogen, we already removed 1 electron from it, and then we have a system of 2 protons and 1 electron. And when we are affecting this model by light, it means we are going from ground state to excited state. And in ground and excited states, the forces on the atoms are different, right? And if in the ground state there is a well-defined interatomic distance which corresponds to a minimum of the potential energy surface, then in the excited state, the minimum can be placed at different value, or there could be no minimum at all. So the way the potential of forces between 2 atoms depend on in which electronic state we are. And when we perform the actual process of sending electromagnetic irradiation onto this molecule, we need to admit the fact that the interatomic distance can be a little shorter or a little longer than it actually is, right? And the transition can happen at frequency that goes directly from minimum to point of intersection, or it can be a little shorter or a little longer. And this process gives noticeable signatures in what we do is instruments if we ever do characterization of molecules. Please vote yes if it all makes sense. Yeah? No one objects? Okay, thank you. And from this thing, from whatever our first meeting, the most important thing that we will speak about position of electrons and position of nucleus and wave function, which we didn't introduce it rigorously in this class, although we should at some point. So wave function, which is amplitude of probability, does depend on both where electron is and what is interatomic distance. So this process of molecular absorption of light naturally depends on this both degrees of freedom, and splitting them and forgetting about either one or second is not possible. Therefore, this concept is advanced because in many cases one can focus on only electrons or only interatomic distances. Okay, so done with review of our first meeting. So we are going to arrive at a picture like this. This image, this picture, is not related to absorption of molecular hydrogen or ionized hydrogen. It will be idealized model related to any molecular absorption in a very rough way. If I would have results for molecular UV absorption of molecular hydrogen, then we would need to exclude this part from our projects, right? So I'm just showing concept, and applying it to practical system will be our task for when we approach closer to the end of the class. So let me make a brief interview. What do you think about this figure, about this picture? Anything you see here and you want to comment, like what are your impressions? Just what you see.
Not sure.
Do you specifically like or specifically dislike anything?
The left graph makes me uneasy. I don't know.
So left uneasy and right is more or less well, easier. So what is on the right, in your opinion?
It's describing modes versus the energy needed to go from the ground state to the next state.
Okay, yeah, perfect. Yeah, thank you. Thank you. Makes sense, right?
I couldn't hear.
You cannot hear? You cannot hear. Okay. I think when we do recording, if you then play it on the maximum volume, you should hear. Okay. Anything you like or dislike about this figure?
I see like waves, maybe.
Waves. Okay. Yep. Makes sense too. Well, any impressions, comments?
The right one looks like an intersection between the ground state and the excited states, and showing like a vibronic modes. The left one, I don't know, it's just spectral.
Okay, yeah, thank you. I think it is really correctly great answer. Let me. Yeah. I'm sorry, the camera was not focused when you were speaking, but next time I'll try to make you a star. Any additional?
No additional at this time.
But, what do you like from observations of previous speakers?
Well, first when I saw the graph, it was a little scary, but I think the trend I'm seeing is on the left graph, as the transition energy is going higher there, it seems to be decreasing for the intensity. That's all I observe.
Okay, yeah, thank you. Middle? Anything you want to observe yourself or comment on a comment?
Okay, it's pretty much same that the intensity is in the first graph, there is the transition energy, probably for the electron, and then absorption intensity, how much energy they are absorbing during the transition period. And change over the absorption intensity with the transition energy, and when it's in the middle somewhere, there is the intensity is higher. So from it gradually increases and then again gradually decreases.
Yep. Yeah, thank you much. Ariana, anything you like about or dislike about previous comments or your own comment?
So I agree with what everyone has said so far. And I guess if I was just commenting on the right graph, I could see a variety of waves and different, looks like nodes maybe, and energy levels.
Okay, yeah, thank you. Let's keep interviews.
Interviews, okay. Looking at the graphs, I could follow with Hamid the intensities, and I see that as well. On the graph on the right, the parabolas look more comforting, but still unsure of the two and how they cross, how that's related.
Okay, yeah, thank you. Haley, now try to teach us how to speak loud.
I guess the thing that sticks out to me the most is the minima in energy on the graph on the right.
So what about them?
That's just what sticks out.
Sticks out? But what is your observation of this minima? So what are their properties, features? Are they same, different? Are they shifted?
So one is lower and shifted compared to the other.
Okay, yeah, thank you. Well, thank you to all speakers. You did my job in explaining this figure. I will summarize. Yeah, let's focus on the. So the logic of theoretical scientist goes from right to the left. The logic of experimental scientist goes from left to the right in this figure. So let's follow experimental logic. So suppose we have a molecule, and we will look on its properties later, that is being probed, being explored by irradiating of light at different frequencies, at different wavelengths. And then when light hits a molecule, it can scatter, like in a blue sky. It can pass through, or it can be absorbed, right? And the quantitative amount of energy or probability of a photon being absorbed at a certain frequency is different. And this dependence of how easily light is absorbed by material as a function of frequency is basically spectroscopy, right? So our experiment that we just run in our heads, that we excite some molecule with different frequency increases, that means wavelength decreases, right? Like, and the units here are electron volts. So here it mostly infrared range, just for comfort of the image. 1 electron volt is 1000 242 nanometers. So 0.5 will be about like 2,500. Just so that if you want to make it connected to any realistic situation. And then suppose we get an experimental data or response of a molecule to increase of the wavelengths shows that there is a frequency at which absorption is maximal, where molecule gets most of the photons, or ensemble of molecules gets most of the photons. There is a lower threshold below which there is no absorption at all. And then there are trends that it increases from threshold to maximum, then decreases down. In addition to this, it is not a continuous band, but it has like fingers, right? It has a substructure. And this intensity of these fingers get bigger, and then lower, and then vanishes to zero. So if you deal with either experiments or computations of absorption spectra of molecules, you may have seen such figures, slightly different, but qualitative feature is about this way. So if you compare this spectrum with typical spectra of atoms, they're very different. For atoms, it is very sharp lines with very narrow thickness, and they are quite offset, as we did on our first meeting, right? You remember. The width of individual line was basically because of the instrument was very cheap. But if we would just upscale a little bit more, the lines will be very, very narrow. If you look for absorption of solids like metals, semiconductors, materials for OLED, organic photovoltaics, they would show continuous bands. So starting from some frequency, it will absorb any photon with certain probability. And molecules have this sub-features. If you pour liquid nitrogen or liquid helium on the sample, this features would come just to peaks, to individual lines. They will be less broadened, right? And the goal of today's meeting is just get an idea what is behind this property, the spectroscopic property of molecules. So now we come to the right figure. To speak about the spectroscopy, we need a molecule with different electronic states, right? When electrons get promoted from one cloud to another, right? And at the same time, we need to admit a fact that one bond if it is diatomic or collection of bonds if it is polyatomic may change, and it is not fixed. There is a probability for a bond to be shorter or longer. So the blue line here corresponds to ground electronic state when electrons are relaxed as much as possible. It shows interatomic distance, potential energy surface, which how energy of a molecule depends if we contract or expand the bond. And then if we accept quantum nature of interatomic bond, there will be different, what you guys called waves. There will be different eigenstates for vibration of this bond. So if the bond is stable, if it is not actually practically vibrates, it will be in the ground state. The energy will be a little higher than the bottom of the potential curve, and the distribution will have Gaussian shape, right? Here, I want to stay as far as possible from any problems in a sense of calculation, even if I lie a little bit in respect to realistic systems. So I assume that potential curves are just quadratic parabolas because they're so much easier to deal with theoretically. Now, if we let our interatomic bond to have more energy, and if it is like quantum probabilistic thing, instead of observing bond going shorter and longer in real time, we would see that it just experiences different eigenstate, where how far these peaks are from each other approximately correspond to amplitude of the oscillations that molecule is gaining, and the positions of peaks correspond where the molecule has, where the interatomic distance has a little bigger probability to stay. So here it means it can be a little shorter or a little longer if one designs an experiment to measure it. If we put more energy into molecule, then it comes to another eigenstate where you see they expand further away, right? So it corresponds to oscillations with higher amplitude. As you pump energy, it oscillates more and more. And ground state, one peak, 0 nodes. Under nodes, we can tell position where this probability function gets to 0 and touches the x-axis. Also, I'm trying to offset these images by the energy it has, which is a little wrong logically, but all natural scientists admit this form of communications. So in this image, we see y-axis is energy plus probability, like comparing apples to oranges. If you go to higher energy, you see the number of eigenstate tells how many times this function touches this horizontal line. So number 2 touches 2 times, number 3 touches 3 times, and so forth. Now, what if we already have a molecule where electronic clouds, where electronic state is excited? So excited electronic state. Then interatomic forces will be different. Potential energy surface will be different. And if we keep electronic state excited, but explore the dependence on interatomic distance, we will go to red potential energy surface, and the progression of eigenstates will be with thin red lines. So if it is electronically excited, but vibration, there is minimal, there is no vibration in the interatomic bond, it will show this Gaussian distribution above the center of this potential energy surface. Make sense? You didn't get tired or upset or irritated yet? Approve? Okay. If we let this electronically excited molecule to get more energy into molecular vibration, it will come to this red line here with two humps. And it will be basically the same progression. Number 0 times it touches the horizontal line. Number 1, it touches once. Number 2, it touches 2. Now, if we consider molecular spectroscopy, if you want to promote our molecule from one eigenstate to another eigenstate, which is basically how molecule interacts with light. It means we are going from one of the thin blue lines to one of the thin red lines, right? And the offset of blue lines and red lines will be the frequency or the wavelengths at which molecule is happy to absorb a photon from the source. And we see that this set of blue lines is discrete and this set of red lines is discrete. So their subtraction is not continuous. There are only certain amount of frequencies at which molecule is able to absorb light. And it corresponds to this experimental or calculated figure. So at certain frequencies, it does absorb light. And you see, we do label these peaks by pair of eigenstates. So here G corresponds to ground, 0 for amount of ground state vibrations. E state stands for excited electronic. 0 stands for 0 amount of vibrations. And the transition from thin blue with single peak to thin red with single peak would correspond to G naught to E naught, and would be the lowest peak. Make sense? And then there could be different combinations of these pairs of orbitals. Before we go to any equations, still we can speak an hour on this figure only. In your next session, in your last 2 months of this course, when you will be dealing with thermodynamics and statistical mechanics, the focus of consideration will be on what temperature it, what heat is, how things are, how the outcomes of measurements of different systems depend when they being heat up or not. So one of the reasons why interatomic distance may start to oscillate with bigger amplitude is temperature, right? So if you pour liquid nitrogen or liquid helium on a molecule, it definitely will come to the ground state. If we put it on a stove, it will keep a little population, some population in the ground, but increase population in this excited, right? But if the offset, or if the frequency of this infrared vibration is low enough, not low, is high enough, then regular room temperature would be insufficient to promote ground to excited. So if our molecule is in the interstellar space, or temperature is close to absolute zero, or if we do low temperature experiment, then we can assume that transitions from G1, G2, G3 have a very low probability. We can basically neglect them in addressing the observed experimental data. So to interpret existing experiments or to predict experiment theoretically without doing it, we can assume that the ground electronic state is also, so the system is has zero vibrations. So we are staying in the lowest quantum state of molecular oscillations. Therefore, in this figure, we have transitions only from G naught to elsewhere, right? You do not see G1 anywhere. But still, this figure, later on, we can see that it corresponds to what most molecules show in their absorption profile. And it still has some additional features that we need to take into account. So, any questions or objections about this figure? Everyone is happy or at least accepting it as is, right? Good, thank you. So here is the equation I'm going to arrive at, so the lower line. I put a chance to complete everything in time into a big danger, but I think if you do another round of interview, there will be some memories among you what we did today. If I just rush through by human nature, we all forget what was. So it's just, I'm going to make another round of interviews and asking what you think about lower equation. And if I would do it as a presentation of a conference, it will be like unacceptable because presenter must explain each symbol. I'm trying to make a shortcut and make you to guess what symbols mean and what this equation is. But I'm just asking you to help me. So any impressions and any ideas what this symbols may mean?
I know that the parentheses is omega, I believe, inside of it, and then summation. But other than that, I'm not fully sure. I didn't do a lot of work with matrices.
Me too. Me too. That's fine. So you observe that it shows a dependence on omega. What is your guess? What omega can mean?
I don't remember.
No. It's not possible to remember because I didn't introduce anything. But if on the previous slide we were talking about absorption spectrum as function of frequency, wavelengths, or energy, like what is your guess how this equation may relate to?
I would guess energy.
Yes. Yeah. Thank you. So energy is Planck constant times frequency, and I was lazy to put Planck constant here, right? So just dependence of frequency, and alpha is intensity of absorption. So it's basically the equation for the left panel on the previous slide. Okay, let's keep. What is your ideas about this equation?
I see energy, V velocity maybe.
No. V should be related to intensity of absorption, right?
Maybe.
No. Okay. Yeah. Thank you. Oh, would you share any wisdom?
I see H bar to reduce Planck constant. I'm not sure if V is potential energy.
Not potential energy. I'm positive. But what about indices? Do you like them? Do you hate them? Do you see any features? Like, are they all uppercase? Are they all lowercase? Are they mixed? What do you think?
This one, the NM, or which one? On the square, which one?
So, any observations about indices?
The squares.
Well, square is just power 2. But do you see anything which may relate to energies of eigenstates?
Energies of eigenstates, DE.
Okay. Yeah. Thank you. Okay.
I can only I recognize the Planck's constant modified, I think, with that slash. I'm assuming it's a change, not the standard one. Or standard, but in a change state. See the absolute value sign there. The matrix dimensions, I'm trying to see if that will be with the 4 terms in there. That's all I can, and then the squared. Other than that, and then there's a delta or change of the resonance there, but that's all I can.
Resonance, is it? Oh, it is written. Okay. And what? So what is delta on your opinion?
The change in something, the change in maybe from one state to the next.
Is it related to like Kronecker or Dirac delta function?
Dirac function, yeah, that sounds right.
Okay, yeah, thank you. Okay, we are accumulating more and more pieces of knowledge. I mean,
So what from this page of paper you gave me, and from look at the equation, I think the energy is from different probably resonance energy or vibrational energy or something like that. and combination of those all sort of energy is the total energy.
Okay.
That is what
Yeah.
my understanding.
Yeah. Thank you, Hamid. Ariana?
So again, I'm also seeing some sort of change in energy. Also based on this paper, it looks like there's probably different vibrational levels maybe. And um,
Okay,
different
yeah.
electronic states,
Okay, yeah.
which is that first half of the equation.
Okay, yeah. Thank you. I like your comments. Continuing the interview.
I'm also seeing how like there's like a combination, like you're looking at electronic states and vibrational states together to hopefully find the total energy,
Oh, okay.
A sigma. And I don't know what else.
Okay. I'm absorbing everything you guys are telling, and some things are absolutely correct. Some can be slightly updated. And I know that Haley has a talent to say correct things, but hide the technical details.
So I think maybe something to do with summation of the energies of the nuclei and electrons at different positions.
Okay, I see. No, I see where your train of thought is going. It is not wrong, but we will refine it together.
Okay.
Any other?
No.
Okay, yeah. Thank you, everyone, for participating in this interview. And I think it will be much better rather than if I just rush through, define things, and we all forget next 5 minutes. So when we discussed the previous slide, left panel, we had y-axis was transition energy, and x-axis was intensity of absorption, right? So here we use symbol A for intensity, and this omega as frequency, which is the same as transition energy. Now, remember the following comment that looks like no one was objecting, which means everyone accepted, that transitions from ground to excited state happen when there is a resonance, when the photon frequency has absolutely the same energy as energy offset of initial and final state, right? You remember it, right? And you can say this was energy of initial, this was energy of final, and this is energy of photon. So if energy of initial minus final and energy of photon are equal, so if you have delta of 0, then it is maximum. And let me make another little, how to say, not interview, but questionnaire. Please raise hands if you're absolutely happy with Dirac delta function. Please show if you never heard about it or you really hate it, or show if you heard something but not sure what. So what's your opinion on Dirac delta function? Down, more or less, down. Ariana? Down, up, more or less? Lower? Oh, okay. I think you are the champion. Everyone else showed either down or more or less. So just briefly, what is Dirac delta?
I don't know how to explain. I can only write.
Hmm?
I don't know how to explain it. I can only write it like out.
Let's go and write together. It will be beneficial for the class, for me and for you. Everyone should wish good luck to Lola. And if you feel bored, your patience is expiring, you can just and you have computers, you can just look in Google, in Wikipedia, like Dirac delta function. Okay, so right now Lola did show the orthogonality relation between wave functions, and it is Kronecker delta. You're doing good things. You are educating all of us. Do not worry. Uh-huh. Okay, so what is I will explain to everyone, and we just need to come to a logical step. What would be the condition between I and J to have 0? No, but mathematically is like I equals J squared. Yes, no? I means cosine of J. Should they be? Okay. Okay, I'll continue. I think should be I equals J. Put J here. Put J. Yes. Okay. Thank you. Okay. Yeah. Many thanks for let's applaud for being very brave. Okay. Do you see what is written and do you recall anything similar? Hamid, I see enthusiasm in your eyes. Oh no. Is there more enthusiasm when we hide the? So what Lola taught to us was the related to Kronecker delta, and I always miss names and mix them. So basically, if you do not want names of scientists, it is a delta function that is related to discrete argument. And this is orthogonality relation related to a complete set of functions in quantum mechanics or in differential equations. The condition here is delta ij equals, then typically one puts bracket and tells if this is a function of two arguments, right? Which is basically a matrix, right? So if the indices I and j are the same, like I equals 1 and j equals 1, I equals 2, j equals 2, if they're the same, then this function equals 1. So Lola was correct. If the indices are different, like I equals 1, j equals 2, it will be 0, right? So this delta ij equals, then we put a dummy matrix and put indices 1, 2, 3, ding, 1, 2, 3, ding. So if the indices are the same on the intersection, we put 1. Indices are the same on intersection 1. Indices are the same on intersection 1. Now, if the indices are different, like 1 and 2, 0, 1 and 3, 0, 2 and 1, 0, 2 and 3, 0, 3 and 1, 0. So you see it's a matrix with ones on the main diagonal. Kronecker delta, discrete. Okay, more or less. If you feel discomfortable, if you think it is nonsense, there is no logic, or you just do not like to memorize it, just raise hand. You'll find a way to replace it with something more pleasant. I'm going to erase it and show another thing. So I erase the word Kronecker and erase everything. So let's replace Kronecker with Dirac. I do not know who Kronecker was, but Dirac was one of the developers of quantum theory. Dirac. So the main benefit of the Kronecker delta, I still need to say a comment about it. Hamid, I'm not going to ask you to write, although I will use the space on the board near you. If you want to replace me, you can keep sitting. You can write instead of me, but I'll do myself for now. So suppose we have a vector like A and B of 2 by 2, right? And what if we multiply this vector by a matrix which has this Kronecker delta's properties? What will be the result of this matrix by this vector multiplication? Huh? Ah, the same. Let's so row by column. 1 times A, 0 times B. A, 0 times A, 1 times B. So by multiplying Kronecker delta by a vector, we get the same vector. So it's one of the properties. Now, what if we want to practice the same property, not for vectors, but for functions? We want analog of this. So suppose we have function of x, and we want a symbol that will reproduce the same function, but of different argument. So like function is like a vector, delta is like matrix. And it is such an object that will help to reproduce the same object.
Same function, but
yes. Yep, makes sense. Okay. And there are definitions, a little bit more rigorous definitions of this thing. So these mathematical things are against human nature. I remember myself sitting for the first time, and my first feeling was hate, because it's too abstract, it's not practical. If someone is thinking about function, let's better draw it, right? So how does delta function looks like? It is not possible to draw it, but one can approximately draw it. So it is a function that depends on subtraction of two things, or even we can put one argument inside. So when the argument of delta function equals to 0, then delta function equals to infinity, and the width of this function is 0. So it's like a peak of 0 width with infinite height. Practically, people typically do x minus x naught, and put here x naught. And then tell, okay. There is another property that is used even more often. So if one has not two independent arguments, just one argument, x minus x naught, multiply by function of x, integrate by dx, and make integral. So when equation under integral is not equal to x naught, then everything will be zero, right? When we come to the point x naught, it will be infinity times very small increment. So based on this intuitive thinking, the result will be function of x naught. So the delta function parses, extracts only one value of a function at the value of argument, right? Like if you have abstract function for any value of x, the delta function will help us to pick only one value. Make sense? Okay, so now let's go back to the equations that we need to interpret. If you over time, we'll just continue. I was planning to go over 60 slides today, but maybe it was not a good idea. So this delta, everyone here was telling delta is variation, is change, right? Because when we do calculus, we use d or delta for like derivative or increment. Here, it's a little different. It's not, the meaning is, it's a function of an argument rather than increment. And it gets infinity when everything under brackets becomes zero. And it helps to parse the value of something in front when this is zero. So we use that there will be noticeable absorption when frequency of light is equal to energy differences of eigenstates. Make sense? And now we come that we need to define energies of eigenstates. We need to have two indices, lower index for electronic state, upper index for vibrational state, right? So we will have, when we do practical things, we will have, instead of M, we will have excited, and here we will have ground. And when photon is not equal to this difference, you'll get just zero absorption, zero signal. If the temperature is absolutely low. If you have elevated temperature, then instead of delta function, there will be something more realistic that will take into account onto thermal effects. Okay, but this delta function will have the same height for each transition. But we started to believe that intensity of absorption will be different depending on frequency. And this factor is responsible for intensity. So it will show that transitions between different pairs of eigenstate can be more probable or less probable. So this intensity must have indices that summarize both initial state and final state. So let's, if this is our initial state, two indices for initial and two indices for final. And then the summation also runs for different initial state, and this pair of indices run for different final states. So this equation brings together contributions from different pairs of eigenstates and makes it a universal relation that will work for any frequency of transition, for any photon, right? Depending on what is actual value of photon, either one or another intensity will work. So this V is not velocity as or potential. It is well, matrix element of interaction between light and matter, or in experimental mindset, it is just intensity of absorption. Intensity of absorption. Okay? Not okay? More or less? Any questions?
Can V pass off as oscillator strength?
Can we go to oscillator strength? It is very tightly related to oscillator strength. It's not literal oscillator strength, but it is very, very close. Yes. Yeah. Thank you for the question. Okay. So I'm going to go to the next slide, and while discussing, I have already forgotten what it is about. Oh, we have more equations, but we are not going to do interview about each of them. So the top equation shows that if our initial is ground and zero, our final is excited and with some state, we can factorize this V onto product of there will be mu times E that I'm going to explain, and then FCF, which has also equation. So FCF is abbreviation for Frank-Condon factor. There are a lot of nice Wikipedia articles and online information that comes on the keyword of Frank-Condon factors. And any textbook on physical chemistry will have this concept. So basically, what the plan today was to speak about Frank-Condon factors. So not 44, no, it should be number 2. So basically, we done introductory part, and now I can start actual lecture, but it's evident that we will not finish in 10 minutes. I'll try my best. So ground, excited, interatomic distance, we need transitions. I'll just go forward. So some of you are taking computational chemistry class this semester and have seen this equation at least once. So what does this equation show? That so first of all, it is the one of the illustrations, one of the implementations of time-independent Schrödinger equation, which means the energy operator. So it's not energy just itself, it's energy operator, often referred to as Hamiltonian. Energy op acts on the wave function, not wave function, and then it reproduces the same wave function and so-called eigenvalue. The eigenvalue problems are main practical concept for quantum mechanics. So everything people do in quantum mechanics are either solving eigenvalue problems or analyze the solutions. So in a broader sense, it's just one of the time independent Schrödinger equations. in more practical sense, related to the subject of Frank-Condon factors, there is a very important thing that typically does not belong to basic quantum theory course. Basic quantum theory course typically refer to wave functions that depend on like 1, 2, maximum 3 arguments. Here, we do have several arguments and of different nature. So lowercase r means electrons, uppercase r means nucleus. So it is eigenvalue problem for a molecule that has both electronic and nuclear degrees of freedom. Okay. Lower cases are for positions of electrons, upper cases are for positions of nuclei. Electrons, nucleus, which means either ions, atoms. So if I do not know if the atom was ionized, and I want just to hide my ignorance about this, or I just want to be very general, I say nuclei, which means either ion or atom, whatever is applicable. Okay. So here I'm going to cover a very advanced concept that also, which is needed for our grasp on the Frank-Condon factor. But again, it is something quite advanced. We will, I plan that we go over basics when we go through implementation. So we make blueprint and then bricks. So the wave functions that simultaneously depend on both electronic and nuclear degrees of freedom are not solvable, no way. They're too complicated. And under they're not solvable, I mean they're not solvable in exact analytical solution with mathematical precision. If we neglect a little bit of precision, if we do tricks, we can get approximate solutions which will get main features of the real life, but will be not exact in mathematical sense. And it is a very standard approach to any, bless you, in nature, any natural sciences. Specifically about quantum mechanics, there are like either 5 or 6 problems that can be solved exactly. And we have much more natural objects. So anything else are approximate solutions, which are correct for analysis of real life and nature, but mathematically are not precise, not correct enough. So our previous equation that was focusing on finding wave function that depends on both electrons and nucleus can be approximately solved in the following way. If we assume that electrons and nucleus interact weakly, not like once per week, but not strong enough. And if we can close eyes for a second and think, oh no, we solve Schrödinger equation only for electrons. Then we close eyes for another second. No, now we solve wave function only for nucleus. So there are tricks that allow to find wave function that depends on electrons only, electronic wave function, and tricks that allow to find wave function that depends on nuclear positions only. It is beyond the goal of this course to discuss these tricks. So I think 2 of the attendees of this class are coming to computational chemistry. This question is discussed in very fine details. But if you get this electronic wave function and nuclear wave function, then approximately the solution, the wave function of a molecule can be reproduced as sum of products of electronic and nuclear wave functions. Nuclear and electronic. So if we are speaking about spectroscopy, it means our initial state is a product of electronic and nuclear wave function, and our final state is product of electronic and nuclear wave function. Therefore, for each wave function, for each state, we have 2 indices, and for transitions from one to another, we have 4 indices, as in this symbol uppercase V, and then lower m, upper M, lower n, upper n. So it's transition from electronuclear state initial, electronuclear state final. Okay, 2 minutes. What does light makes to matter? How photons interact with molecules? Although we are very short in time, I would like to ask your opinion on what is dipole moment. Please raise your hands if you are so happy about concept of dipole moment and you can explain it. Show down if you never heard about dipole moment or you hate it, or show if you are more or less heard about polar molecules, dipole moment. No one risks to fully say yes. I think Ariana was most enthusiastic.
No. Dipole moment. Doesn't it have to do with like bond polarity?
Okay, yes, very chemical point of view, good.
And then like positive and negative charges.
Exactly. I do not need more. Thank you. It's excellent. So if we have a molecule where positive and negative charge are a little imbalanced, right? And then we put this molecule into electric field, no matter what's the reason like, then the molecule will rotate, right? In such way so that the line connecting positive and negative charge will align to the direction of electric field, right? If we enforce molecule to be a different angle, it will have some energy, right? If it naturally goes along field, the energy minimizes. So this is interaction of electric field and polar molecule and dipole. The same concept is applied to interaction between light and matter, because light is electric field that changes over time. I think we are done with, we should respect the schedule, because maybe you have other classes or some different plans, but we'll continue where we left. And I suggest you keep this little things that I thought will be quiz and complete them either at home or during our next academic lecture, like next Monday during the class, because I didn't show the actual thing that would help to solve it. If some of you already read through the notes, it's great, but we should be fair to everyone. And when we meet each other on Wednesday, we will not do the thing. We will do MATLAB training, right? So we will continue this academic part on next Monday. Okay, thank you much. Have a nice day, and I'll stay here to answer any questions. But everyone is welcome to leave or disconnect. Stephen, I was always thinking to ask questions to you, but I was so excited with those who are physically in class. Next time I try to involve you into the interviews.
That's fine.
Okay, thank you for the permission. Do you have any, Stephen, do you have any questions right now, or it's okay to finish, to disconnect?
No, I don't have any questions right now.
Yeah, then have a nice day, and I'm going to end this Zoom link.